Hello, my name is Pedro Toledo. I'm a PhD student in Polytechnic Torino. I'm going to present the work entitled as a digital-based analog processing nanoscale CMOS IC for IoT application, and my supervisor is Professor Paulo Crovetti. Now I'm gonna go through the other address research questions and problems that I have faced during my PhD. All the ultra-low voltage digital-based circuits for IoT application that I have designed and fabricated and measured, and our achievements in conclusion. Internet of Things is a concept that all the things around us will be connected to the internet, and in order to enable that, ultra-low power systems are needed, including the analog interface. In this scenario, during my PhD, we have tried to advance analog IC design strategy in order to fulfill all the requirements for IoT applications. When we need to implement an IoT system, likely we're going to have to design a digital part in order to process the information, and the analog and RF part in order to sense the external world and transmit the desired information. However, along the years, in this plot in the right, we can see that along the years there is a huge gap between the digital and analog improvements. At the same page, if we take a look in the analog design flow and digital design flow, we can see that the digital design flow is more automatic and it helps the portability across the technology. During my PhD, we tried to answer the following question: could we implement the analog blocks using digital techniques? In this way we can get the advantage of the digital improvements. The first block that we used in order to answer the previous question was the operation Transconductance amplifier. Here in left we can see the traditional way to implement it. Here in the right we can use the pair of the buffer in order to implement the same functionality, which is to amplify the differential signal and reject the common mode signal. To do that, we need, besides the differential pair of buffer, we need a common mode extraction to cancel the common mode signal, and the output stage in order to be sensitive only to differential signal. In collaboration with National University of Singapore and Federal University of Rio Grande do Sul, Brazil, we have fabricated the digital-based OTA in 100 nanometer CMOS technology, and it only consumes 500 picowatts, enabling in this way several IoT applications. In order to improve the signal-to-noise ratio and also to get rid of passive components, a new version of the DIGOTA has been proposed, as you can see in this slide. This new topology has been also fabricated in 100 nanometer CMOS technology, even though it consumes a little more power, but it has better SNR and lower area. We have also proposed a new model for this kind of topology. In this way, we have created design guidelines for the DIGOTA. In this video above here, you can see the digital TA working properly, only being powered by a very small silicon photodiode. If you want to see the whole video, you just have to QR code here. To further prove the power efficiency and the area efficiency of our proposed DIGOTA, we have used it as a building block of a biomedical amplifier, as you can see in this slide. We have already fabricated and now we are measuring. To conclude, during those last 3 years, we were able to explore several new ideas regarding digital-based approach. We have published 14 papers plus 1 poster. We have had several collaborations with top universities around the world, and we were also able to get some best papers awards.